So as students, we've all been faced with a very similar problem. You're sitting in class, the professor's at the whiteboard writing down the most important formula for the entire semester, and the entire time they're deriving this formula, they're standing right in front of it, blocking it where nobody can see it. So what, as students, do? We either wait for the professor to step out of the way, and then we furiously scribble down as much of the information as we can, but while we're doing that, we can't actively listen to any explanations, any further information that the professor may be giving. Or what normally happens these days is as soon as the professor steps aside, everyone pulls out their cell phone, takes a quick picture, and then listens to the professor. But in a classroom with 50, 70, 100 students all doing this at once, the complete flow of the classroom is disrupted. The professor gets distracted. The students aren't actually paying attention even though they think they're doing the quick fix. And the whole just flow of everything gets destroyed. So as a team, what we wanted to do was find an inexpensive and portable solution to this problem. My name is Brian Wilkerson. I'm the project lead. With me I have Todd Martin, who is our hardware lead, Taru Verma, who is our software lead, and Andres Alvaredo and Angel Ortiz, who are our software engineers. Together we are Team Link, and we wanted to create a device that attaches to the back of a whiteboard marker very easily that would use a triple-axis accelerometer, a triple-axis gyroscope, and a triple-axis magnetometer to record the acceleration data and the orientation of the device, and then output an image file that would be very easy to send to students through email or post on a service like e-learning, so that the students could actively pay attention and take the notes that they needed to without having to worry about making sure that the formula that they will need is exactly right. And all the steps showing why this formula is important are there. As we went through our project, we discovered a current limitation with the technology today and the inertial measurement units. As a single sensor IMU, you cannot really grab dead positional reckoning. So as you can see with, it's a little hard to see, but like a bee, it drifts and then it moves and you don't get a very accurate reading. So that's what we spent a lot of our time doing, was trying to see if we could come up with some software way that we could actually correct this data and make it look better. You can especially see the drift in our third D. It starts out really great, looks like a D, and then it just kind of goes off into infinity because the IMU just cannot figure out where exactly it is on the board. And that's our presentation. Do we have any questions?
So what is the accuracy you can get out of this?
The accuracy can range from about 20% to about 80%, as you can see, like these letters.
So it's not practical.
Not practical.
No, it's not practical for it to use in a classroom.
So do you have any plan? I mean, is there any way to improve on that, or this is like a dead end?
Well, comparing it to current other devices, many devices have used multiple sensors, but the problem with that is that with adding more multiple sensors drives up the price. So those, like the VR headsets, cost, I don't know, $300 to $500. So that defeats the purpose of our design, to make a cheaper positioning device.
So right now our goal was to get it implemented under a budget of $50 to $60 right now. And the main bottleneck in our project is the sensor. Maybe with higher quality sensors we can focus on getting data faster and which is more accurate. And other approaches that we can use is add additional sensors to the board, but at the cost of sacrificing portability. So if we can have RFID sensors, or if you guys know of Google's project Soli, where they're using radars, short-range radars to track movement. If we can figure out how to place them on the corners of the board, so to basically triangulate, that would complement the data that we have collected here. So we have used optimizations in the form of Kalman filters. We have used complementary filters where we mixed acceleration data with gyroscope data and magnetometer data to get as accurate as we could. And so far, this is the best we can proceed. So with additional sensors, and as we can see, because we can make some sort of recognition, maybe neural net, deep learning net can take a few hundred of these samples and then automatically generate an ASCII character instead of a shape. So it can it can recognize that you're trying to write a D and then eventually translate that to an ASCII character, maybe not a shape. So that's a direction we can go into that will satisfy the scope of our project, and we'll get ASCII letters instead of, say, just discrete shapes.
One last question?
Yes, how many professors did you ask that would use this if it were accurate?
Everybody we talked to said
Yeah,
yes.
I mean, my father, I told him the idea. He's an engineer, and he was like, I would definitely use that just because at the end of every meeting that we have, everyone stands up and it's shuffling in front, taking a picture real quick. I actually had a professor that had slides, wrote down on a piece of paper everything that he did in class, then took pictures of each individual page of paper and posted it on e-learning. That's somebody that would instantly use something like this just because it would cut out so many individual steps.
Okay.
One, really last one.
So you can purchase marker boards where you write, you press a button, and it actually generates a hard screen. The cost is significantly more.
And the portability. So that was one of the big things was, I mean, at this university, I don't know how many classrooms we actually have, but it's in the thousands. And each classroom has normally 3 or more boards. That means a whiteboard, a smart board in every single classroom for every single board. And I think that the cheapest one I found was $500. So when you extrapolate that out to an entire university setting, I don't think very many universities are going to foot that bill.
And as opposed to those boards which cost over $500 to $1,000, our device, we can build it in $70. And it's a great proof of concept that we can at least get some recognizable data, and then using, right now our approach was to use filters to generate an image, but then maybe if we can move to some machine learning based techniques, then we can generate more accurate information, and then it'll be more useful to professors.
Just a real quick one, your 9-degree of freedom inertial measurement unit, I assume that was just one IC, and what was that?
It's actually was made by, it's a SparkFun block that connects into our Intel Edison system on a chip that was actually the brains behind everything.
No, it's actually in.
Yeah. You can kind of see the different blocks. You have the Intel Edison here, and then a board for communications, and then you actually have a battery and the actual sensor embedded in there.
Okay.
So do you have to connect that to?
No, it has Wi-Fi
So
capability.
it has Wi-Fi capabilities, Bluetooth capabilities. You can connect it via USB, micro USB, and that could also do a download for you and charge it. Our battery has about 12 hours battery life before we
He
stop
was kind of
looking.
back to the question that he asked before, which was, my experience is, you're fumbling looking for a marker to use, which one works, and does everyone have to have that hung at the back of it?
So
Because
the-
I could just see somebody picking it up and writing, and your information.
Our final design would actually use the connection on the back of the marker that you just actually just pull it off and stick it back on to a new marker, because we've all seen in classrooms where they go through a lot of markers. So you could just pop it off and put it back on one and just pick up again where you were.
All right.